Hello and welcome. It's SFU Math 232. It's Brenda. We're section 6.3 now, Kernel and Range. Okay, so like all of these lectures, there's vocabulary. There's a lot of vocabulary in this course, so we're going to have a few more words that we're going to define and use. Kernel. What does it mean, kernel? Okay, so if we have a linear transformation from Rn to Rm, then the kernel of t, which we'll denote using that symbol right there, ker of t, is the set of all vectors that map to 0. So that's what this says here. Kernel of t equals all the vectors v, such that when you transform v, you end up with 0. Okay, so let's just take some examples to see what's happening here. Find the kernel of the 0 transformation from Rn to Rm. So our domain is Rn. And then we're asking which vectors in Rn map to 0 under the 0 transformation. Well, that's all of them, right? So the transformation, the 0 transformation, like that, maps every vector in every vector x in Rn to 0. So the kernel is all of those vectors. So I would write that then. Therefore, the kernel of t is Rn. Okay, let's try one that's maybe a little bit more complicated. Here's one. Find the kernel of t, R3 to R2. Given that what the transformation does is produce a 0 for the first coordinate in the codomain and produces the second coordinate as x1, x plus y plus z. Okay. So we're saying, we're asking that same question, which vectors, okay, so our domain is R3. Domain is R3. And we're saying which vectors in R3 map to 0, 0. That is because our codomain is R2, and that 0, 0 is the 0 vector in R2. Okay, so that's going to be the vectors. It doesn't matter. This guy is going to be, the mapping produces 0 there all the time. And then the other condition means that x has got to be equal to minus y plus z. Okay, because if x is equal to minus y plus z, then we'll get, we can pick any value for y and any value for z, and then we force x to be minus y minus z, or minus y plus z in brackets. Okay, so that is, I'm saying the values of x, which will map to 0, will be all the ones that will look like this. Okay, because what happens here, this vector here, these vectors here, well, let us how to say this. Let us take a look at it this way. We could put this transformation into a matrix. What does that look like? The transformation indicated by by a matrix is going to look like this. It's going to map always the first component. Okay, it looks like this. It's x, y, z, x, y, z, and that looks like this. 0, x plus y plus z. And I want to know, excuse me, which one of those map to 0. So I want to know what vectors which vectors x, y, z will map to 0. So this is a statement of when does ax equal to 0. So I can go through and you'll get that there. Okay, we know how to do this. Figure out which vectors map to 0. Okay, so that means the kernel in this example is this set right here. So the kernel of t in this example here, let me give myself a little bit more space here. Kernel of t is exactly this thing that I've written here. The set of vectors s minus 1, 1, 0 plus t minus 1, 0, 1, where s and t are real numbers. Those are all the vectors. All those vectors will be mapped to 0 because they have this condition that x plus y plus z is equal to 0. All possible combinations of that. You can see that because that the sum of those numbers is 0 in both cases. Okay, let's take another example. We have a transformation that maps R2 to R2, and it's the orthogonal projection onto the x-axis. What is the kernel? Okay, so we're imagining taking any vector, and we are projecting it onto the x-axis, and we're asking for which vectors do we end up with 0. So you can see what must happen is that any vector on the y-axis, any vector here, when I project it down, will end up being the origin there. So any vector along the y-axis will give a 0 result under this orthogonal projection. So the kernel of t is the y-axis. Or we could write that alternatively like this. Kernel of t is the set of all vectors that look like this. And that is a parameterization of the y-axis. Okay. How about what happens when we reflect? So let's just draw a picture. We reflect about a line through the origin having angle phi with the x-axis. We'll just draw that. We've got this line here. There's phi. And we're going to take vectors and we're going to reflect them across that axis. So for example, if I had some vector here, v1, I would reflect it and it would end up over here. That would be v1 prime, the reflection of v under this transformation. Okay, so what is the kernel? So the only vector whose image under reflection is 0 is the 0 vector. I don't, when I'm just looking at this geometrically, if I pick any vector here, any vector, and I imagine reflecting it about the line, there's no way that a reflection is going to cause it to suddenly disappear and become a point at the origin. So I would say that this way, the only vector whose image under reflection, and that's their reflection, is 0. Okay, so I would then claim that the kernel of t is the set containing the 0 vector. Okay, so the kernel is simply which vectors, when acted upon by the transformation, result in 0. Okay, so what is the kernel of a matrix transformation Rn to Rm, where A is an M by N matrix? We sort of had a bit of a hint of this coming sooner. This is the solution space of AX equals 0. Okay, so let's just take an example, what we just saw, and just look at it in a slightly different way. For example, we have t from R2 to R2, and we did that where t was orthogonal projection. To say what the transformation is, otherwise this is going to make sense. Orthogonal projection onto the x-axis. And we said that the kernel of t. By looking at it geometrically, we claim that the kernel of t is the y-axis. Okay, so the matrix that performs projection onto the x-axis looks like this, like that. And so what we can do then is take a look at what this solution space of this is, like that. We see that y is free, and I'm gonna say y is t, and then we see that x is 0. So we would then conclude that the solution here, the solution to this augmented matrix right here, Ax equals b, the solution is x. In this case, x is, we're thinking of x like this, is x and y. X would be t, y is free, and x is 0. There it is. And that is the same parameterization of the y-axis. That was as we had before. So we would say then the kernel of t of A is the set of vectors like that. T is a real number. Okay, so we have another word for this when we're thinking specifically of the matrix. We say that the kernel of the transformation defined by the matrix, we call that the null space of A. And it is the solution space Ax equals 0. So I could say the kernel of the transformation defined by A is some vectors, or I could say that the solution space of Ax equals 0 are those same some vectors, or I could say that the null space of A is those same vectors. So there's 3 ways really of saying that. Then we have further that if we have a linear transformation from Rn, if it's a linear transformation, then the kernel of that linear transformation is a subspace. It's not just a subset, it is a subspace. So knowing that it is a subspace, we would have then that in R2, the possibilities for the kernel are for the kernel of T are the following. We know what other possible subspaces are in R2. That it could be the origin, the 0 vector. It could be a line through the origin, or it could be all of R2. Those are the only possibilities. Okay, so we have another theorem here, and that is if we have a linear transformation T that is mapping Rn to Rm, then T maps subspaces of Rn to subspaces of Rm. Okay, that's basically saying that if your domain S is a subspace of Rn, and then you perform your linear transformation on it, you end up guaranteed to be ending up with a subspace in Rm. So your collection of vectors that are in your range will for sure be a subspace. So this is saying that T maps subspaces to subspaces. Okay, so let's just, show an example. We could have, for example, in R2, we could have a line through the origin that is a subspace in R2. But the only possibilities of subspaces in R2 are the origin, the 0 vector, so the origin, the 0 vector, lines through the origin, or all of R2. So let us think that our domain is this line through the origin. So that's a subspace. So this is our domain. And it is, in this case, in R2. We're going to do an R2 to R2 mapping. Then we apply our transformation to the domain, which is that line. And what do we end up with? Well, there's actually 2 possibilities. depending on what that transformation is. We could end up with some line like that. That would be the range there, some line, or we could end up with this guy here. Those are the two subspaces that are possible if we start with that domain. You know, we can't end up with all of R2. That would not be a function. You can expanding up from a line up to the whole of R2. It won't work because it won't be a function. Okay, so we've brought in this word range, just sort of without being completely rigorous yet. So let's fix that. So we want to know, what is the range of a linear transformation? The range is, well, we're going to denote it by this symbol here, RAN of t. And it is the image of the entire domain. Okay. So we'll recall from earlier that the range is a subset of the codomain. This is a subset of the codomain. Okay, and we already know that it's a subspace. The range is a subspace. So we, well, we know that the mapping preserves the subspace. So the range of T is a subspace under a linear transformation. Okay, let's take some examples to clarify these concepts. What is the range of the zero transformation? So we're asking, what is the image of every vector in Rn under this transformation? Okay, so I will claim here that the range of T is the set containing the zero vector. I mean, no matter what input I put in, I get out the zero vector. Well, this is that. So then the whole possibility of all the possible outputs that I can get from this function is the zero vector. So this guy here is the this is the image of every v in Rn under T. Okay, and that's precisely 0. Okay, let's take another one. We saw this one, or we saw this transformation already. We found what the kernel was just in a couple slides previous. Now what we're asking is, what is the range? So I am looking at vectors, the output vectors that will have the format 0 and then something else here. And I can see that given all possible inputs, I can have that number that's going to be there, x plus y plus z, is going to be all possible numbers. So the range of t is the y-axis. We have, I mean, let's just write our transformation this way. We've got this 0, 0, 0, 1, 1, 1. Just like that, we multiply it by x, y, z. We see that we get 0 and x plus y plus z. So I'm then looking, okay, I'm thinking all possible guys here, that's R3. All possible guys there, and then what do I get out? Well, I'm going to get out things that are 0, and then I will be able to get every possible number here. So the range of t is the y-axis. And that is equal to t in R. Okay, that's the y-axis. It's parameterization of the y-axis. Okay, that's our range. All right, so now let's look at another one. We got orthogonal projection again. Again, we found the kernel of this thing already. Now we're asking, what is the range? Okay, so let's just remind ourselves what the kernel was. The kernel of t for this transformation here, orthogonal projection onto the y-axis. The kernel of t is sorry, the projection is onto the x-axis. The kernel of t is the y-axis. That's a line. The range of t, well, we're projecting, I mean, we're taking vectors any vector we want in R2 and we're projecting it onto the x-axis. What are the possible results? I mean, that is all of the vectors along the x-axis. So the range of t is the x-axis. So that we're going to write like this. The range of t is equal to t times 1, 0, t in R. That is the x-axis, and you'll notice that that's also a line, a subspace. Both of the kernel and the range there are subspaces of R2. Okay, third example. Now we're going to have a reflection about a line through the origin. Okay, and so I'm going to claim here we have some line like that, and then what we do is we consider all the vectors in R2. That guy's going through the origin. So this angle here is phi, and then we take a vector b, and we reflect it about the axis, reflection. And so I just try to get that roughly right. It looks to be about up here, somewhere like that, such that this angle here is equal to this angle here. And then that will, and the length is preserved under reflection. So this is going to be v1. Let me just call this, sorry, let me call it v prime. The image of v under t. Okay, so I claim that here that the range of t is all of R2, because I can always find a vector v such that given some other vector v prime, I can always find the preimage. So I consider v some vector in R2, and I'm like, can I find a vector in R2 that will reflect and give me that? And I say, yes, I can. So the range of t here is R2, and let us just remember here that the kernel of t was the 0 vector. All right, so we can actually be a little bit more methodical about this than just looking at it geometrically, and we'll have a couple of theorems that allow us to get the kernel and the range without necessarily drawing a picture and thinking about which vectors are going where. And that first one of those is that the range of a linear transformation defined by a matrix is the column space of A. Okay, I'm going to sort of do quote unquote a proof here, but really what I'm going to do is sort of just give I hope a clear explanation of why this has to be the case. So let us consider what is this linear transformation. T A of x is equal to ax. That is the linear transformation defined by A. And when I multiply A by x, I'm going to get some output B. What we want to figure out is all possible values of this. Okay, that is going to be our range. And we have we allow here as an input all possible vectors that are of size n. So this is all possible vectors in Rn. Okay, how do I know it's Rn? I know it's Rn because of that n right there. So let's just take a look at what this means in sort of in a little bit more detail. I have a matrix A, and it looks like this: A11 all the way to A1n, because it has n columns, and then it goes down here to AM1 because there's m rows, and this guy over here looks like that. Okay, and I could think of that like this. As a collection of columns. So I'm going to rewrite it like this so I see what I'm thinking of. I'm thinking of it like this, as a collection of columns. There it is, a collection of column vectors. So I am thinking of A as a collection of column vectors. And they are like this, C1, C2, like that, up to Cn. Okay, so I've got that this one here is C1, this one here is C2, and all the way along here, this one here is Cn. Okay, so I'm going to now write that again. I'm going to write A like this. I'm thinking of A like this, C1, C2, Cn, where each one of those C's are column vectors. Okay, so now let's take a look at what it looks like when I multiply by x. Get those column vectors, and I multiply by x, which I'm going to write like this in its component form. There it is. So that will look like this: x1 times c1 plus x2 times c2 plus dot 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 plus xn times cn. Okay, so these are all the possible b's that I could get. I can let this guy be anything, any vector in Rn, and all possible b's will be of this form. So all possible outputs, which we've typically been calling b, are linear combinations of the column vectors. Okay, so let me just rephrase that. All possible outputs, that is the range of the transformation. All possible combinations, all possible outputs, the range, are linear combinations, or all the linear combinations of the column vectors. There. Okay, so we don't have to, geometrically necessarily look at and be thinking, okay, I'm thinking I have this input in, say, Rn, and now I'm going to try to figure out where exactly all those guys go and see what kind of space that looks like. I don't have to do that. I can simply find the column space, and that is the range. Okay, next thing, if we've got linear transformation, we can ask the usual two questions we often ask, the uniqueness and the existence question. So is every vector in Rm an image of at least one vector in the domain? So is every vector in Rm, we'll recall that this right here is the codomain, and then there should be an and here. Is every vector in Rm an image of at least one vector in the domain R? Okay, that's the existence question. The uniqueness question: can two different vectors in the domain have the same image? So that's asking this kind of a question. If we have ax1 equal to b1 and ax2 equal to b2, and we have that b1 is not let's see, hang on. Can two different vectors have the same image? Oh, the same image. Let me correct that. So I'm asking this: is it possible to have this? ax1 is b1, and then ax2 is also b1 when x1 is not equal to x2. So do two inputs produce the same output? That's the uniqueness question. Okay, so we have more words to keep track of this sort of stuff. And so we're going to use the words onto. Transformation is said to be onto if its range is all of Rm. Okay, that is for every vector in the codomain. We can find a vector in the domain such that the vector in the codomain is a transformation of that vector in the domain. Okay, it's onto. The whole thing is covered. Okay, I'm going to say it that way sometimes too. So what you can do is onto means the whole thing is covered. So think of it this way. You take a blanket, putting a blanket, think of, let's see how I would write this. Think of taking a blanket. Okay, let's say throwing, because that's more exciting. Throwing a blanket, that's going to be the range, onto a bed. The bed is going to be the codomain. Okay, if the bed is covered, by the blanket. Okay, you can't see any portion of the bed. So if the bed is covered by the blanket, then the transformation, then the throwing, right? Then the throwing, that is the transformation, is onto. Okay, one-to-one. Transformation is one-to-one if it maps distinct vectors on Rn into distinct vectors on Rm. Okay, I'm just going to draw a little picture for that one. It means that if we have some vectors here, these are vectors in Rn, and over here we have our codomain Rm, and we have guys here like that. Okay, it means that this guy is going here, this guy is going here, this guy is going here, this guy is going here. Okay, we do not have in the one-to-one model, we do not have this situation. Okay, that would be not one-to-one. The two of them going to the same one. Okay, that's what it means to be one-to-one. So we can say one-to-one is if the transformation of x1 is equal to the transformation of x2, we are guaranteed that x1 is actually x2. That is another way of saying it. There's a nice picture of this in the textbook, actually. So check that out on page 300 of the Busby textbook. There's a nice picture. It sort of to indicate to you what it looks like for something to be one-to-one. Okay, so there's two ideas here. We've got two ideas. We have onto, and we have one-to-one. And I will sometimes write one-to-one like this, one-to-one. Okay, and then we have a transformation. And so a given transformation can be neither. Okay, so a transformation can be neither one-to-one nor onto. It can be one of them and not the other, or it can be both. So those are the possibilities. There's four possibilities. Okay. The other thing to alert you to, I don't believe, I'm not going to be 100% about this, but I do not believe your textbook uses this term, but it is the case that onto is also what is called a surjection, and that one-to-one is also called a injection. Okay, and if you look up in Wikipedia, take a look in Wikipedia at the definition of injection. You will see that it tells you that it's one-to-one, that's saying, but it has a very nice picture. So there's a nice picture that shows you a function that is onto, a function that is one-to-one, and then a function that is one but not the other in both ways, and a function that is both. And if you can reproduce that drawing yourself, then you will have the idea clear in your head. What does it mean onto, and what does it mean one-to-one? Okay. All right. Let's take some examples, see if we can figure this out. We have a number of transformations, 4 different transformations listed here. Let's see whether we can say that if they are onto, one-to-one, or neither. Okay, so let's just go in order. A here, this is a transformation, orthogonal projection onto the x-axis. So I'm just going to appeal to a picture here. Let's line this up here. I've got one vector there, v1. I'm going to get a second vector here, v2. And then I'm going to project both of those down onto the x-axis. And they will both, the projection of v1 and v2 will be exactly the same. The shadow of both of those, when I'm sort of shining a light source down like that, is that red vector there on the x-axis. So first off, you can see immediately from looking at this that it's not one-to-one. Right? We have two vectors on the input which are different that give the same output. No, it's not one-to-one. Okay, next question. The codomain is R2, and when we project onto the x-axis, do we cover all of R2? No, we don't. I mean, only vectors, our output is only along the x-axis. So all of R2 not covered. Therefore, it is not onto. Well, it's neither. So this one is an example of neither. It's not one-to-one, and it is not onto. All right, let's take a look at B. We've got what is B? A reflection at angle phi with the x-axis. So this is this guy here. We have some line here. I always have basically the same line when I do a reflection. Okay, we have some line here making an angle of phi with the x-axis, and then we reflect about that line. So we can take, for example, we could take some vector here and reflect it about the that line there, and it would show up over here. That's not v1. I've been calling that v prime. The image v prime is the image of v under the transformation of reflection about a line through the origin at angle phi. Okay, so can we, if we consider reflecting every possible vector in R2, do we end up with every possible vector in R2? And I say, yes, you do. Because if I give you one of these guys that's a reflection, you can find me one of these guys. So I could kind of pick any vector over here, which I would consider to be, let me do this in a different color. Say I took one here and I would consider this to be W prime. So this is a reflection, and I would ask, oh, can I find a vector that reflects to that? And I would say, oh yeah, I can. That would be this guy roughly here. So that this angle here is equal to this angle here. And that would be W, same length as W prime. So I'm always going to be able to do that. So all of R2 is covered. So this is an onto transformation. Okay, does each vector produce a unique reflection? Yes, it does. So each v prime, my output, has a unique v, an input, and so this is also a t is 1 to 1. So this one is both. So we had the first one, this first example, it's not 1 to 1, it's not onto. The second example here, it's onto and a 1 to 1. Okay, next example, C. We're taking a transformation from R2 to R3. And the transformation looks like this. Okay. No, so I think it's clear that it's 1 to 1. I mean, if I have a unique x and y here, that same unique x and y show up there. Okay, so it is 1 to 1. Is it onto? No, it's not. And it's not onto since R3 is not covered. Okay, I'm not able to get, I mean, let's just find an example. No vector in R2 maps to 1, 1, 1 in R3. So this vector here in the codomain of R3 is not reached by this transformation because this component is always 0 and here it is 1. So this is not possible. Okay, what does this sort of look like? I mean, this is a mapping that looks like this. You have R2, your domain is R2. So that's this guy here, R2, the whole thing, R2. That is our domain. And then it maps into R3, which I'll draw like this, like that. And we have X and Y and Z. But where does it map these things to? It just maps them to this plane, the XY plane there. Okay, so we're not able to find anything that maps, for example, to that point right there. Okay, so it is not onto, but it is 1 to 1. So that's one and not the other. And let's take a look at the final example. That is, it's a transformation that is mapping from a domain of R3 to a codomain of R2, and the transformation looks like this. And we simply basically are taking all of R3, throwing out the Z component, and just providing the XY plane. Okay, so it's not 1 to 1. It's not 1 to 1. I mean, you could see, for example, that XY1 maps under this transformation to XY, and XY2 also maps under this same transformation to XY. So two inputs map to the same output. It's not 1 to 1. It is, however, onto. It's onto because all of R2 is covered. Okay, let us get some methods of calculating these sort of things. Here's a statement, a true statement. It's a theorem, and it's telling us that if we have a linear transformation, then if t is 1 to 1, that implies that the kernel of t is 0. If the kernel of t is 0, that implies that t is 1 to 1. Okay, so just going to make a couple of statements that gives you the idea of the proof. You might want to take these little statements and then fully flesh them out into a nice proof for yourself. But let me just say it this way: going in the forward direction, we assume that t is 1 to 1. So we say t 1 to 1, and then we also know that t is linear. And then that means that we have that t of 0 is 0 by the linearity. We know it's 1 to 1. So that means x equals 0 is the only vector for which t of x is equal to 0. So therefore the kernel of t is the 0 vector. Okay, then we go the other way. We assume that the kernel of t is the 0 vector. And then we take x1 not equal to x2. And that means that x1 minus x2 is not equal to 0. And that means x1 minus x2 is not in the kernel of t. So then I take t of x1 to x2, like a t of x1 minus x2, and that is t of x1 minus t of x2. It's linear, and then that is not 0. Therefore, t of x1 not equal to t of x2. And that means t is 1 to 1. Okay, so there's that. We're building to getting a couple of more lines on our unifying theorem. Okay, so here now let us take a look when we're considering our transformation captured in a m by n matrix, and saying that the transformation is 1 to 1 then is the same as saying that the null space of A is the 0 vector, and that is the same as saying that the linear system AX equals 0 has only the trivial solution. And then saying that our transformation defined by A is onto is the same as saying that the system AX equals B is consistent for every B in the codomain. Okay. Suppose we've got a transformation from Rn to Rm. It's linear, and that m is less than n. So we're going from a higher dimension down to a lower dimension. Can t be 1 to 1? Think about this for 2 seconds. Commit, and then see if you're right. Okay, so let me just, while you're thinking, e.g., we could be doing a transformation from R3 down to R2. Can it be 1 to 1? No, it cannot. Okay, no, it cannot. Okay, AX equals 0 has more, I mean, we're going from R3 to R2. So AX equals 0 has more unknowns than equations. It's not square. And therefore has non-trivial solutions. So then more than one vector maps to 0. I mean, the 0 vector is going to map to 0, but then we're guaranteed that something else also maps to 0 because there's a non-trivial solution. So we're done. Okay, next theorem. Now, important thing to note, this statement is about Rn to Rn. So we're talking now about a square matrix. If we've captured the transformation in a matrix, it is square. And it's a linear operator. We're in linear algebra. And here's the statement here. If t is 1 to 1, then t is onto. If t is onto, then t is 1 to 1. That is the case when we have Rn to Rn. Okay, if we have Rn to Rm, then you cannot make this statement. So what is this a restatement of? Really, this is a restatement of this. Imagine A n by n. We have a square matrix, and we have this AX equals 0 has only the trivial solution. That is the same as saying that AX equals B is consistent for every B in Rn. Okay, that's what this statement is the same as this statement when we think of if we're thinking of the transformation as a matrix. Okay, all of this stuff now can be added to our ever-growing unifying theorem. Okay, and how are we doing that? We're adding these two lines right here. That is, if we have a matrix, an n by n matrix, then each one of these statements is equivalent to all of the other ones. So if I say that I have a matrix and the transformation defined by the matrix is onto, then I can immediately, for example, claim that the determinant is not 0. Likewise, I can tell you right away that lambda equals 0 is not an eigenvalue. I can then say that, oh, it's an invertible matrix. There's a lot of statements I can make that actually at first glance don't seem obviously related. Like to say something like A is invertible and then say the transformation given by A is onto may not seem completely obvious. So, we're now building a whole host here. There's 12 of these guys now on our unifying theorem, that each one of these statements is equivalent to all the rest of them. I mean, 12 of them already. Okay, so where will it end? We've nearly used up half the alphabet. It's kind of like naming hurricanes. Hopefully we won't have to extend up to the Greek alphabet. Okay, so that is it for today, and I'll be back with section 6.4 shortly. Thanks, guys. Bye.